stream status is poor. Neat. Alright, I'm gonna eat real quick. Yeah? I'm about to start revision. Who's that? I'm saving things up. What's up?
Bad version of the song Walking.
This is a start. I used to make bad animations and I got good.
No, it looks like he's basically his legs is snapped.
I'm just setting things up.
rounds. Blocks with 30. Run up on me. I'ma do you dirty. Shut the fuck up. I will fucking laser you with alien fucking eyes and explode your fucking head. I wanna grab the shoulders and shake, baby. Who's we? Who's we? There is no we. We. Who's we? There is no we. We. Who's we? There is no we. And I'll handle it.
Come to my house and park on my street driving this vehicle. I mean, what the hell is wrong with you? I'm really asking.
Nothing. I'm sorry.
What is it, Skylar? What the heck? What was...
Okay, lunch is. Neat. Would you like to see Dora and Chucky cooking up every single Tuesday or something? And we're all.
Okay, I'm coming. Mine. Me!
Oh, just a second, excuse me. Yeah?
Can you collect Adam for me?
On what day?
What time do you normally come back here? This Thursday.
Thursday, same time.
You can't do it, you can't do it split. You stay at school till school time. I will send him some work, but I've got to go into the office on Thursday. Thursday's my day off. Swapping my days, so I'm not working on Monday next week.
Yep.
Could you do it?
I could do it on Thursday, yeah, but it's gonna be
What time will you be back?
probably around 12:40ish.
Okay.
Takes me about an hour to get home. It's probably easier anyway to do that. I'm gonna be revising now. I've just finished. I'm gonna revise. No, thank you. Right. Ba da 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 ba da da. I guess you wonder where I've been. Ba ba. I guess you don't know. I can let you know. By the hands of you, but I can't let it go. Guess you wonder where I'm on my mind. Going through the pine. But I can't let it go. I guess you wonder where I've been. Do should find out. Right. No. Finish chemistry homework due tomorrow. Right. I guess you wonder. What's up? Go ahead.
Your dressing gown.
Uh-huh.
From Adams.
Mm-hmm.
You're going to Yaya the Wolves
When?
weekend.
Oh, during the weekend or
Yes,
Friday?
on Saturday.
On
Back
Saturday.
on Sunday.
Okay.
Well, you not just so you know, as part of your schedule. Because we had planned.
I planned around it. Don't worry. It's
Well,
fine.
we planned it ages ago. Like obviously, Uncle was away, and
I had a feeling that it was gonna come up, so I planned around that. No need to worry.
but then we won't be going for another 2 weeks, maybe 3. But as we get used to it.
Yes, yeah. Marvel vs. Capcom 2 New Age of Heroes. I'm gonna take you for a ride. I'm gonna take you for a ride. I wanna take you for a ride. I take you for a ride. I guess one must learn how to become comfortable with their own company. Let me search this up actually. Not how to. No. I need to think. Okay. Okay, I'm gonna put this to one side. So this is my physics work. physics notepad. Let's put that to one side. I'm gonna take you for a ride. I'm gonna take you for a ride. Okay, so that works. Adam. They got any cheese or something? Streaming. Move. I'll get you that. I'll get it for you, okay? Yeah. Okay, equilibrium constants homework. I'm gonna take you for a ride. Alright, let me search up this one thing real quick. Disturbing a peace. Just look into my eyes. Mm-mm. Just drug on a piece. Um. Oh, 10 minutes already passed. Five minutes.
The true artist, so let's get it, see what we can uncover. What that defines your world, gives you truth and life. What that excels, special enough to guide your way through this shadow world. The true artist, so let's get it, see what we can uncover. Let there be someone there to share truth and love. Who really cares?
We begin welcome. Oh my god. Let me finish off that thing, and then we'll have a break. It's literally winter. Da, 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 da. Another well done. man. Need to wake up. Da, ba-da-da, ba-da-na-na-na-na. Ba-na-na-na-na-na-na-na-na. Da-na-na-na-na-na-na-na. Alright, break time for me. No. Ah. Da. Right. Listen to this.
Let us redefine relaxing, working.
break is over. Oh man. My chemistry homework away. Oh man. Ugh, so cold. And I tried to put something else on. It's just it's either too cold or too warm for my liking. And that's really annoying if you ask me. Alright. Upland. Oh, so Upland is so good, you say? Okay, fine. Let's see how this goes. Bro, what? Oh, this is paper free. Oh, no. Other mechanics. Okay, so let's go to some exam. No, let's relearn some stuff. This bores me. Let's try something.
When you write, your tone influences how readers respond. For grammarly, highlight your text and type how you sound.
Did I watch this?
One condition to be true in order for something to be. So, let's say I'm swinging a conker around my head, and I have my piece of string going towards me until there. Let's say that the conker's velocity, v, is going that way, as it's in front of me there. Now, I want to change the direction that it's going in. I don't want to change its speed at all. I just want to change its direction. You should remember from Newton's second law that if you have a resultant force, you have acceleration as well. But acceleration doesn't have to mean change in speed, because change in velocity can mean change in speed or change in direction, because velocity is made up of both of those. The only way that I can apply a force in order to make sure that this conker doesn't speed up or slow down is towards me. I could push out and that would have the same effect, but of course I've just got my piece of string here, so we're going to forget about that. They're at 90 degrees to each other, they're at right angles to each other there. Let's go a split second into the future, and my conker is now here. Is its velocity going the same way that it was? No, because I have pulled sideways on it, 90 degrees to the velocity, and I've changed the direction of its velocity. It's still going the same speed, just in a different direction. If I pull with the same force downwards like so now, if I pull downwards on this conker now, then I'm going to be pulling a little bit in the same direction as the velocity, which means it's actually going to speed up. That's not what I want at all. Again, the only thing that I can do is pull 90 degrees to its velocity. And this will carry on all the way round until it forms a circle around me. So the only condition that you need for circular motion is this. Force is constantly acting at 90 degrees to the object's velocity towards the centre of the circle. And that goes for any sort of circular motion that you have at all. That could be a satellite going around the Earth where the satellite's weight and the force of gravity is actually pulling towards the centre of the Earth at all times, obviously. As a car goes round the roundabout, the friction between the tyres and the road, that's also acting towards the centre of the roundabout at all times. We call this force centripetal force. Now you might hear it called the centripetal force, but hey, I'm British, I call it centripetal force. A centripetal force is one that is always acting towards the centre of the circle. Now you might hear centrifugal force. Centrifugal force is a bit of a weird one. It's the sort of fake force that you think you're feeling as you're being pushed out. Say if you're on a roundabout, you feel like you're being pushed out of the car. But in fact, all you're feeling is the centripetal force pushing you in towards the centre of the circle. So there's no real such thing as the centrifugal force. Now, there is an equal and opposite reaction force in any situation, of course. You could call that the centrifugal force, but we don't. You can see that the force is always 90 degrees to the velocity. So we could say the velocity is always at a tangent or tangential to the object path. In other words, it's always at a tangent to the circle. We can see that there. Put a ruler there, that's on tangent, that's the velocity, and there, you get the idea. What would happen if my string snapped all of a sudden, so there's no more tension, there's no more centrifugal force? Some people think that the conker would actually fly out in this direction. That's not true at all, is it? Because that means that we're creating a velocity out of nowhere. The conker at this point is going this way. So if the string snapped right then my conker would fly off in that direction. Things always fly off at a tangent if the centripetal force is all of a sudden removed. So with a bit of help from Planet Coaster, let's see what this looks like in reality. Or not quite reality, but you get what I mean. So we have a thrill ride here, and each of these capsules is undergoing circular motion and is constantly accelerating towards the centre. Let's put on the arrow showing the centripetal force for one of these capsules. Now the centripetal force here would be the tension in the metal bar that is connecting it to the hub. We also see this with the chair swing ride, and the people in their chairs get flung outwards. They would go flying off at a tangent, but the tension in the wires keeps them accelerating towards the centre, but not getting any closer, so that makes them go in a circle. Now on a loop-the-loop on a roller coaster, the centripetal force is the support force exerted on the cars towards the centre of the loop. Using only half a loop, we can demonstrate what happens when the centripetal force is suddenly removed. The centripetal force is there as it goes round the circle, and then at the top the velocity is going to the left, and the centripetal force is removed because it runs out of track, and therefore it no longer accelerates towards the centre and just flies off to the left. So that's where the GCSE ends pretty much. Let's have a look at some A-level stuff. There's our object going in a circle. Let's go around this way here. And the force, as per usual, is acting towards the centre here. There's its velocity at that point in time. Now, in order to be a circle, that means that the object has to be the same distance away from the centre at all times, and it's at a distance r. That's the radius. So we know that it has a speed v, it's r away from the centre of the circle, and we have a force F. Now, we know that the object is constantly accelerating towards the centre of the circle, because that's the way that the force is pulling. That has to be true. If a force is pulling in a certain direction, that's the way the acceleration has to be going as well. But what's weird is that it's not getting any closer to the centre of the circle. So a satellite going around the Earth is constantly accelerating towards the centre of the Earth, but it's not getting any closer. Kind of weird. The acceleration that something experiences going around in a circle is equal to v squared over r. That's velocity squared over the units work out. We end up with meters per second squared. Putting this into
Simple
F
harmonic
and A,
motion.
we end up with F equals mv squared over r. And that's the main equation that you're going to be using for circular motion. Now, later on in gravitational fields and magnetic fields and electric fields, you're going to be equating this force to other forces as well. So you're going to be using this equation a lot, especially probably in the second year of your A level. So this force could be the tension in a string that's making something fly around in a circle, or it could be equals to an object's weight if it's going around in an orbit around the Earth, or it could be equals to friction, or it could, like I said, be equals to force due to an electric field or a magnetic field as well. What can we do with this then? Well, you're usually given the mass of an object, and you're probably given the radius as well, or you might be asked to figure that out. A lot of the time, you're not given the speed, but instead you're given the time that it takes for an object to go round in a full circle. And we know that a time period is the time it takes for anything to complete a full cycle, and we call that t. That's seconds. It's a capital T, not a little t. Don't forget,
If I remember
as well,
correctly,
frequency
V is equal to 2
is one of the
pi
time
r
periods,
o
vice versa
t.
as well. So you can be given the frequency, and you have to use that instead.
V is also equal to 2
We'll use this in a
pi
second.
r f.
Something speed is equals to distance over time. The time that we're talking about is the time period here, and we have a full circle. So what's that going to be? 2
V, so V is equal to angular speed r.
over t. And using frequency instead, we get 2 pi f r. This is where we introduce
Let's go.
something new. 2 pi f has its own special symbol. That's an omega, sort of like a curly Greek W. This is called angular velocity, or angular speed. And we measure it in radians per second. Why? Because we have 2 pi, that's the amount of radians in a full circle, times f, which is frequency, which is hertz per
Angular speed.
per second as well, s to the minus 1. So angular velocity is just telling us how many radians per second an object is doing. So we can see that v is omega r, or omega, depending on how you say it. Omega is also going to crop up in simple harmonic motion as well, so it's worth getting your head around. Now let's consider a satellite going around the Earth, a geostationary satellite. Here's the path that the satellite is taking. Now if I ask you to draw where the radius is, you might be tempted to draw on here an arrow going from the surface, but of course with circular motion the radius has to go from the centre of the circle, so this is the centre of the Earth. Now what do we know about a satellite that's in a geostationary orbit? We know that it's above the same point on the Earth's surface, and that has to be above the equator, obviously, because if it's anywhere else it's not going to go in a perfect circle around the Earth. So we know that the time period for this to do one complete orbit of the Earth is 24 hours, because it's following the Earth's rotation. Times up by 3,600, that's the number of seconds in an hour, and we get 86,400 seconds. The radius of this orbit, I can tell you, is 4.2 times 10 to the 7 meters. That's 42,000 kilometers. That's from the center of the Earth.
Well, awesome.
And the mass of this satellite is 50 kilograms. What if I ask, what is the centripetal force felt by this satellite at any given time?
Alright, cool. We'll pause this. As F is equal to mv squared over r. Okay, so we know V. So we just need to find V. pi r over t squared over r. So basically we're just going to do m 4 pi squared r squared over t r 4 pi squared r m over t. So okay, 4 pi squared times 4.2 times 10 to the 7 times 50 kilograms, I mean. Then we have to do it over what's it called again? Alright, newtons.
We know from earlier that F is mv squared over r. Now we have m, we have r, we don't have v. In order to find out v, we could do the whole 2 pi r divided by the time period. That gives us a speed of 2.05 times 10 to the 3 meters per second. Then we could pop that back into there and we could find the force that way. We could do that, but you might notice that there is a bit of a shortcut. Because we know that V is omega r, we can pop that back into here. And we actually end up with F equals m omega squared r. So in fact, we do not need to know how fast the satellite is going. We don't need to know its actual speed. All we need to know is its angular velocity. And in order to find that out, let's do m 2 pi over t squared times r. Omega is 2 pi f. It's also the same as 2 pi over the time period. So square that. So 50 times 2 pi divided by 86,400 squared times the radius, which is 4.2 times 10 to the 7. That gives us a force of...
Oh, I made a mistake. I made a silly mistake. I made a very silly mistake. .1 newtons. I forgot the square of a t. Okay.
That's how big our centripetal force actually is. What about if we've got a plane and it's coming towards you, and what it's doing is that it's banking. In other words, it's going in a circle. It's not yawing at all. All it's doing is...
I need to find the best way to learn math and science. It's brilliant.org. Whoa. Brilliant has thousands of interactive lessons.
Pulling upwards, as it were, at an angle. So it's going in a circle like this, and that's the radius of its path as it goes in a circle. And we know that if it's pulling up, then it must be providing a force in this direction here, perpendicular to the wings. Let's say that we know this angle here to be theta. If it's going in a flat circle as well, we also know that whatever component that we have going vertically must be equals to mg. Finally, we know that this component, the horizontal component of this force, must be equals to mv squared over r, because that's the force needed for circular motion. By the way, this works for a car going around a banked track as well. It's just that the force isn't up thrust, it's just the reaction force from the track. So, what do we know this force to be? Well, we know if we have this angle here, then to find out what the resultant is, we're not turning through the angle. So we're going to use sine. If you haven't seen my easy vectors trick video, then have a look at that. So we can say that this force is going to be equals to mg divided by, because we know it's going to be bigger, by sine theta. Turn away from your sin, turn away from your sine. So that's how we can find the resultant force from the weight. We also know the force can be calculated using this centripetal force as well. It's going to be mv squared over r divided by cos theta, because we're turning through the angle in this case. If the force can be calculated using the weight, and it can be calculated using the centripetal force, then we can actually equate these two things together. More often than not, you'll just have to rearrange this to find then the radius of the plane's circular path, or the speed that it's travelling at. See if you can have a go at rearranging to find the speed. Pause the video if you want to go with that.
Okay, neat. F is equal to mg over sine theta. F is also equal to since basically it's the same force, cos theta we're trying to find the speed here, aren't we? Is equal to v sine theta over r. Vr cos theta is equal to v sine theta. V squared is equal to no, because of a where did I go wrong? Alright. That's fine. I'm just trying to go through this. Relearning centrifugal force. Is equal to gr. So v squared tan theta is equal to gr v squared over gr tan theta. Then nicely v is equal to root gr over tan theta.
Is it mixed rubbish?
We know that the m's disappear. We've got f on both sides. What we can also do is take sine theta and to the other side here. And we end up with g equals v squared over r times, now we have sine theta divided by cos theta. You might know from this, that actually gives us tan theta. Finally, if you want to get speed from this, all we have to do is rearrange this, and we end up with v squared over r equals mg divided by tan theta. Finally, taking the r to the other side and square rooting it, we end up with the square root of gr over tan theta, so square root of the whole thing there. Let's go back to our loop the loop. So here's the track coming in. Now let's have a think about what the support force is from the track at each point as
Support
the
force.
car is going round. So we have it here, here, and here at the top. Not too concerned about this side, because it's going to be exactly the same as this side. Now let's just have a think about this bit here first of all. Whatever the support force, I'm going to get S, of the track has to be, we know that weight is pulling downwards, so we don't really care about that because the support force is going towards the middle. The support force is only needed to provide the centripetal force. So we can say S equals mv squared over r at that point. However, what about here? Here we have a support force as well, but the support force also has to hold the car up. So more support is needed for the weight. So in this case,
mg plus it.
the support force is going to be mv squared over r, but also it has to counteract the weight as well. What about up here?
mg.
Well, this time weight is pulling down, so it's almost like weight is actually contributing to the centripetal force. So actually, less support force is needed at the top because weight helps. So that means that S, in this case, again, is providing the force for circular motion, so there's mv squared over r, but this time the weight is actually helping. So we can take off mg. So when it comes to any question like this with vertical circular motion and weight is involved, just think, is weight helping or is it hindering? If it's hindering, then the support force needs to be greater. If weight is helping the centripetal force, as it were, then we can take it away from the support force. So I hope you found this useful. If you did, leave a like, leave a comment down below if you think I've missed anything or you have a question, and I'll see you next time. You won't.
Greatest. Smallest. Alright, so we have simple harmonic motion, but we have some minutes left. Yeah, you mind just bursting in? But close the door at least. Hold on.
Collecting my headphones.
Oh man. 5 minutes. Then we're going back to. Circular. the last time I'm checking my phone. Until goodness knows when.
So my daughter Alyssa did A-level maths. She achieved an A star. She's 13 years old.
SHM, or simple harmonic motion, describes how things move when they oscillate. Let's say that we have somebody on a swing, and here they are at equilibrium. That's where they would be if they weren't swinging. And that's the midpoint, isn't it? Because once they start swinging, the swing should be symmetrical about that point. What if this person wants to start swinging, and they get pulled up to this position here, and they're ready to be let go? When they're at equilibrium, do they feel any force trying to bring them back towards equilibrium? No, they don't, because they are at equilibrium already. But when they're up here, they do feel a force that's trying to pull them back towards equilibrium. Is that always going to be the case? When they're the other side, is the force still going to be towards the left? Well, no, because we know that gravity, their weight, is going to try and pull them back towards equilibrium again. It might seem a little bit obvious, but it's actually very important that you know the conditions needed for SHM. And the first condition is this: acceleration, therefore force 2, acts in the opposite direction to displacement. We say that to the right is positive, to the left is negative. When they're displaced to the right, the displacement is positive. Which way is the force and acceleration pointing? Negative. When they're the other side, the displacement is negative, but the force is pointing in the positive direction. So this is correct. Acceleration acts in the opposite direction to displacement. If I lifted them higher, would they experience a greater force or a smaller force to begin with? Well, they should experience a greater force, shouldn't they? As they come back towards the centre here, as they're in equilibrium, we said that there's no acceleration back towards the centre because they're already at the centre. So what we find is that acceleration, and therefore force 2, is proportional to displacement. So those are the two conditions needed for SHM. If number 2 was true, but number 1 wasn't, then that would mean that acceleration would be pointing in the same direction as displacement, and the person on the swing would be gone before you know it. So let's make an equation for this then. Like we said, acceleration is proportional to displacement. We're going to give displacement the letter x. Try and make a curly x instead of a multiply sign. But we know that satisfies condition number 2, but we know it needs to be going in the opposite direction as well, so we put the minus in front as well. To turn this into an equation with an equal sign, we need to introduce a constant, and actually for SHM that ends up being this. The minus is there, which is going to be equal to 2 pi f squared x. F being frequency, 2 pi f being angular frequency or angular velocity, also equal to minus omega squared x. Now, when we talk about frequency, we are talking about complete oscillations per second. So, if we're starting at the top, then that means going over to the other side and coming back again to the same position. That's one complete oscillation. Same thing if we started in the middle. To do one complete oscillation, we'd need to go to the left, to the right, and back again, not just to the left and back again. So, frequency, that's complete oscillations per second. X is displacement, I should say from equilibrium. I'm going to write equilibrium like that, EQ little m, makes it a little easier. And also we need to talk about time period. That's for one oscillation. How do we find the time period for the frequency? Well, they're reciprocals of each other, one divided by the other one. Amplitude, we're going to give that the symbol A. That is the maximum displacement from equilibrium. In other words, you can't get any further away from equilibrium unless you have another external force involved. More on that later. So when it comes to any SHM, it could be somebody on a swing, or it could be a pendulum, similar to this, or it could be a mass on a spring. We need to understand what's happening to the displacement, force, acceleration, and speed, velocity at any given time. So I'm going to draw myself a little grid here. So looking at our swing here, I'm going to give you the 3 positions here: left, centre, that's equilibrium, and right. I wonder if you can tell me what the displacement, the velocity, the acceleration, and the force is at each of these points, whether they're maximum, 0, and then to the left.
I want to test something. I'm gonna take you for a ride. I'm gonna take you for a ride. I'm gonna take you for a ride.
Or the right. But instead of left and right, I want you to use negative and positive. So, 10 seconds, pause the video if you have to. See if you can figure those out. So, displacement, nice and easy.
Okay, so position at the left, so displacement is going to be at max. Then so velocity will be at 0. Acceleration. No. The velocity will also be at its max. No. Velocity will be at 0. Acceleration will be at 0. F will be equal to 0. Then at center, velocity will be at its maximum. X will be equal to 0. A will be equal to 0. Yeah, but V will be its max. F will be equal to actually wait. Yeah, F will be something. F will be equal to 0. No. A will be at its max. Yeah, A will be at its max, and V will be at its max. Then F will be at its max. X will be at minus X. V will be equal to 0. A will be equal to 0. F is equal to 0.
First, when it's at the left, we know it's at max. And that's
Let's go.
negative. At the center,
Oh, yeah,
it's 0.
negative. Okay,
At the right, it's max.
positive max.
But in the positive direction. Let's go for speed. When it's at the left here, what's
0
the speed at that point? Well, it's actually 0. Same at the right.
max
We get the max speed
in the middle.
We're going through the center. Or whether it's going to the right or the left, well, as it's going from left to right, velocity is going to be positive and vice versa. So we're going to say positive or negative depending on which way it's going. What about the acceleration? When do we have no acceleration? We have no acceleration
Over
at the
here,
center.
and it's maybe
No
max
acceleration
positive
towards the center.
and
So
max
we're gonna do that.
negative.
When it's at the left, which way is the acceleration pulling? To the right, and it's at a max there.
Positive.
Look at this, displacement and acceleration going the opposite way. We know that's going to be true. And here as well. That's on max, it's going to be negative. Whatever the acceleration does, the force is going to do the same. So we know it's going to be the same as the acceleration there. Well done if you got those right. So what about if we drew a graph?
Okay, let's see.
showing what's going on with displacement, velocity, and acceleration at any point. This side is positive, this side is negative. This is the midpoint, this is equilibrium. Let's start.
Oh, you get
with
sine graph, don't you?
displacement. With a swing, we're going to start at a maximum, so we're going to say that it starts there, follows.
Oh,
This
so
shape
it's
here.
cos graph.
That is, well, it's supposed to be a sine wave. So this is displacement. Now, if I drew a dotted line joining the peaks together, what am I showing? I'm showing the maximum displacement, and that's my amplitude. So you should be able to see that already that the displacement at any point is going to be a fraction of the amplitude. And we started at maximum, oopsie, so there's going to be cos 2 pi ft. As per usual, if anything changes sinusoidally, then it's either going to be cos 2 pi ft or times sine 2 pi ft. So all we're saying is that displacement is going to be some fraction of A, the maximum displacement where we started them from. What about acceleration? Well, we know that from our conditions, the acceleration is always going to be in the opposite direction. Now, I'm not drawing this to scale, so please don't get the idea that acceleration is as big as the displacement, but I'm just drawing it to show you the shape. So it's always going to be doing the opposite, isn't it? Slightly trickier one to do is velocity. Well, let's have a think about it. Here we start at the right hand side, so that's our swing, and it comes through to equilibrium like that. So at this point here, at equilibrium, the swing is going from right to left, so the velocity is actually negative. So we put a cross down there. Here it's going to be 0 because we're at the top. We know that speed is 0 at the top, and then we can just follow that pattern through. So we can see that all three of these things are 90 degrees out of phase, or pi over 2 radians out of phase with each other. Displacement is 90 degrees out of phase with velocity. Velocity is 90 degrees out of phase with the acceleration. Displacement and acceleration, 180 degrees out of phase with each other, which makes sense given our conditions earlier on. If you really want to get mathsy with it, the gradient of the displacement function actually gives you the velocity. They're derivatives of each other, but you don't need to go into derivative and all that jazz, but it is worth knowing the gradient of the displacement line gives you the velocity at that point. Here we have a negative gradient, so that means that we have a negative velocity. Here we have a 0 gradient, so we have a 0 velocity. Here we have a positive gradient, so we have a positive velocity. That's how it works. So let's just go back to our equation for acceleration real quick. We had acceleration equals minus 2 pi f squared x. What's going to be the max acceleration then? When do we have max acceleration? Is it at equilibrium? No, because we know we've got no acceleration at that point. It's going to be at the maximum, or rather at the amplitude. So we can say that we have the max acceleration when x is a, when the displacement is the maximum displacement. Velocity is a bit of a trickier one. Now you don't need to know the derivation for this, but the velocity at any point is going to be plus or minus, because it can be going to the left, it could be going to the right. 2 pi f and the square root of the amplitude squared minus the displacement squared. So let's say that the amplitude was 5, the displacement that we're looking at is 3, going to be 25, take away 9, that gives us 16. Square root of that is going to be 4. That's how we find that out. When do we get maximum speed? We get maximum speed at equilibrium, because at the maximum, at the amplitude, we get no velocity, no speed for a split second, and then maximum speed as it comes through equilibrium again. So that's when x equals 0. What does that give us? Plus or minus 2 pi f square root of just a squared. In other words, a. Now this is very useful when it comes to pendulums or swings. Pendula? Let's go with pendulums. Useful with pendulums, given the height difference. But on that note, if we are talking about a pendulum, and there it is.
I'm assuming that's going to be A.
At amplitude. There's my height difference. But that isn't my displacement. Where is my displacement? This is my displacement here. That's my x. Now you might see a bit of a problem with this. In reality, this is going to be a curved path because it is kind of like circular motion. But all of this SHM stuff is a good approximation for a pendulum that is displaced less than 10 degrees. So if that's 10 degrees there, then it's all good. If it's more than that, then we say that the model starts to break down a little bit. That's why whenever you do an experiment with this, you don't want to be putting a pendulum out there. You just want to be bring it out just a tiny bit. You're going to find out that actually displacing it a little bit compared to a lot is, as it turns out, more accurate. So the question is how do you find the amplitude if you're given the height difference instead? You have to go for energy. what do you know? That at this point, it doesn't have any kinetic energy, but it does have gravitational potential energy, mgh. When it comes back to equilibrium, all of that has been turned into kinetic energy. So it's half mv max squared. M's cancel, you can find out your v max. Once you find your v max, you can find your amplitude if you have the frequency. One more small thing, what is the tension going to be for the string or whatever that's holding this up? Well, if you haven't seen my video on tension versus weight, then it's worth having a look at that. But we say that tension would be equals to mg in order to merely hold the mass on the end just there. But because it's actually making it go in circular motion at the points as well, we need to add on to there mv squared over r. And yes, that v there is going to be the v max.
Now, what would the graphs for energy look like for a pendulum or a mass on a spring or anything undergoing SHM?
So what we can do is draw just simple axes, energy on the y-axis, then we have displacement on the x-axis, and we have positive and negative. Then also we're going to have amplitude as well, so maximum displacement negative direction, and then the same the other side. So let's have a think about kinetic energy first. So where is kinetic energy going to be greatest? Think about a swing, think about a pendulum or a mass on a spring. It's going fastest when it goes through equilibrium.
So yeah, equilibrium. So it's going to be like, and it's going to be its lowest of that.
Reaches amplitude. We know that for a split second it stops. So I know that it's going to do that as well. So joining these up, we end up with this shape here.
Parabola shape.
So that's kinetic energy. What about potential energy? Well, when a pendulum or a swing is at equilibrium, it's not going to go anywhere, so it has no potential energy. So it's going to be the opposite. And then at amplitude, again, it's going to be the opposite to kinetic energy. So this is what we have for potential energy. Potential energy increases as we get further away from equilibrium. So potential energy. And that can be any kind of potential energy, really. With a pendulum, it's gravitational potential energy. With a spring, it's elastic potential energy. There can be others as well. So what about total energy? Well, we know that in any system, total energy is equal to potential energy plus kinetic energy. So if we add all of these up at every point, we end up with just a straight line. So in theory, total energy should stay the same. But that's only in theory. That's only if there's no forces resulting in energy being taken out of the system, energy being taken out of the oscillations. Therefore, amplitude stays the same. In reality, we can have damping forces or actually driving forces as well, which can reduce and increase amplitude respectively. If you want to know more about that, have a look at the next video. So how can we find out what this total energy is equal to? So we could find that out from potential energy maybe, because at amplitude, doesn't matter which one, potential energy is equal to the total energy. So if we could find out the potential energy, then we've automatically got the total energy in the system. So if it's a pendulum, we could use, e.g., mgh to calculate the potential energy and therefore the total energy. But more often than not, we will use, instead of potential energy, we'll use kinetic energy. So at equilibrium, it's the kinetic energy that is equal to the total energy. We can see that because there's no potential energy, so all of the energy is kinetic energy. We saw earlier that V max is equal to 2 pi f a, or omega a. I've just switched from k to ek, excuse me, same thing. This is equal to half mv squared. So therefore we could say that ek max is equal to half mv max squared. So then all we would have to do is stick this into here, and we can find out the maximum kinetic energy at this point here. And once we find that, well, that's the total energy. And we've also just proven why these lines are curves, because we can see that kinetic energy is proportional to velocity squared, and so because velocity depends on displacement, that means that energy is proportional to displacement squared. Quite often in questions you'll be asked, what is the total energy of the system? And you'll be like, I don't have an equation for total energy. But just remember that if you can find out V max of the system, you can find out the maximum kinetic energy, and that's the same as the total.
E max is equal to 2 pi f a. K E max 2 pi f a.
Energy of the system. So I hope that helps. If it did, please leave a like. If you have any questions or suggestions, put them in a comment down below. See you next time.
Chegg's expert-supported AI explanations go beyond giving you the answer and get a step-by-step breakdown of your problem right away. You always have the option to send your...
So let's talk about two specific cases of SHM. First of all, we have ball on a string, and you've seen that already. We're also going to be looking at mass on a spring. Now, there are some people who claim that all physics can be summed up with balls on strings and mass on springs. And to be honest, they're kind of right. A heck of a lot of physics and the physical world relies on simple harmonic motion. Now, you don't need to know how to derive these. You're given these equations for the time period for each of these. The time period for a ball on a string, that's a pendulum, is equals to 2 pi times the square root of L, that's the length of the string, over G. That's the gravitational field strength, or the acceleration due to gravity, depending on what you want to call it. For a mass on a spring, it's similar because it starts with 2 pi times the square root of mass on the spring divided by the spring constant itself. So very similar equations, but quite different as well. Notice what this equation doesn't have in it, mass. That's weird, isn't it? It doesn't matter what mass the thing on the end has. The surface area does kind of matter in reality, but more on that later. But this could be a golf ball, or it could be a car, and it doesn't matter, it would still have the same time period. Notice that it doesn't have an amplitude either. So again, it doesn't matter whether you displace the pendulum that much to begin with, or that much to begin with, it's going to have the same time period regardless. That's why we have pendulums in some clocks, like grandfather clocks. They start off swinging a lot, their amplitude is big.
It's downstairs, it's downstairs. And it's, yeah.
The time it takes for that pendulum to
There's no
swing.
staples, no.
But it does have G in, so it would change on different planets because you have a different G. So what about the mass on a spring? We do have mass in this case, so time period does depend on what mass you put in there, but it doesn't have G. Again, it has no amplitude, so it doesn't matter how far you pull down this mass from equilibrium, it's still going to oscillate up and down with the same time period and the same frequency. So it doesn't matter what the gravitational field strength is. You could be in space where there's a G of 0. You're still going to have the same time period for a mass spring system. So how are these things proportional to each other? Well, 2 pi is a constant, so we can say that the time period is proportional to the square root of L over G. If G was constant, time period would be proportional to the square root of L. If the length was constant, then that would mean that T would be proportional to 1 over the square root of G. If you haven't seen my video on proportionality yet, go and have a look at that if you're unsure of how to deal with this kind of question. So here's a question. If the length of your pendulum doubles, how is that going to affect the time period? Well, we know that the time period is proportional to the square root of L, so that must mean that the time is going to go up by a factor of root 2. Let's have a go at another one. If G got weaker by a factor of 4, what would happen to the time period? Well, here we have T is proportional to the inverse of the root of G, and we're dividing by 4. If we're dividing by 4 but that's square rooted, then that means ultimately we're dividing by 2, but that's on the bottom, so altogether the time period would go up by a factor of 2. These kind of questions for pendulums and mass and springs crop up all the time in multiple choice in your exams, so it's worth getting your head around the whole proportionality thing for these two equations. Same over here, time period is proportional to root m, or T is proportional to 1 over the root of the spring constant. Just one more question, let's have a go. If you had a spring which is 4 times stiffer, what would happen to the time period? Have a go at it yourself.
Alright, let's try something along those lines then. One wrong. Two. Oh, yes. Three. T1 be equal to T 0.5T.
So if k is going up by a factor of 4, that means that the square root is going up by a factor of 2, but it's on the bottom, so that means that the time period is going to halve. How can we find out g experimentally from the pendulum? Well, we do, as per usual, need a straight line graph. What are we going to put on these two axes to get a straight line graph? Let's have a look at our equation again. You can see that t is equals to this, but we want g ultimately. Let's rearrange this. I have t over 2 pi equals root over g, squaring the whole thing. I have t squared over 4 pi squared equals L over G. Flipping the whole lot and rearranging it, I end up with G equals 4 pi squared L over T squared. So what am I going to put on these axes here? I'm going to put L, I'm going to put T squared there. I'm going to change the length of my pendulum, and I'm going to measure the time period, and I'm going to plot one against the square of the other. So to find out G, I do 4 pi squared times the gradient. What about the other side? Very similar to over here, we end up with T squared over 4 pi squared equals M over K in this case. If I want to find out K, this is rearranging this, I end up with K equals 4 pi squared times the mass over T squared. It's going to give me 4 pi squared times the gradient. So what I'm going to put the mass here, I'm going to put the time period squared down here. Now when you do these experiments, in both cases, you're going to take lots of readings. I would say take 10 or 20 oscillations. So let's say that we're doing 10 oscillations, worth having a fiducial marker, so a straight line with the pendulum, so you can see when it's crossing equilibrium, and the same thing with the mass and the spring, so you can see when it's passing that point. What you do is let the pendulum swing, or let the mass and spring go up and down, and then ready and start, and that's 0 oscillations. 1, 2, 3, 4, and you're going to keep on doing that until you get to 10, and that gives you your time. For 10 oscillations, let's say that took 5 seconds, so that means that your time period is going to be 0.5 seconds. Same thing with your mass and your spring. Let it oscillate, and then when it hits the midpoint, go 0, 1, 2, 3, 4, all the way up to 10. That way, you're drastically reducing uncertainties introduced due to human error. I hope you found that useful. If you did, then please leave a like. If you have any questions or think I've missed anything out that you'd like to see, then please leave it in a comment down below, and I'll see you next time.
Huh. That's depressing. That's just depressing. Man. Time to read some Demon Slayer. I got 10 minutes left of revision. Right. Time to work. 10 minutes this time, because let's start this.
And welcome back to this US Open office plan.
Miller just lobbed a message way over Jones's head using some technical jargon.
Ooh.
No, so far we talked about simple harmonic motion when we just have the accelerating force back to the equilibrium. We call that the restoring force. Well, what if there were some other forces involved other than that force that is proportional to the displacement? So let's split the sheet in half again. On the left-hand side, we're going to look at damping. This is when we have a resistive force. Such a force always has to oppose the motion of the object that's undergoing SHM. So always in opposite direction to velocity. So I love pushing my little niece Seren on her swing, and once I lift her up to this amplitude, I can just let her go and she's going to start swinging like this. Now, if there wasn't any air resistance, what would happen? Well, she would just keep on going forever and ever and ever if there weren't any drag forces. Because you've got the restoring force getting greater and smaller, and she'll just keep on going. But in reality, we do have air resistance. If there was no air resistance, then I would just draw a sine wave that would stay the same amplitude. But in reality, what's going to happen? Her amplitude is going to get less. You can actually sort of plot how the amplitude is going to decrease over time. We call this light damping. Light damping is going to affect the time period ever so slightly, but we pretend that it doesn't really. That is just enough force to keep the time period the same, but it is going to reduce the amplitude. So eventually Seren's going to come to a standstill like that. But it's time for Seren to go inside, and she's swinging away like that, and I want to bring her down nice and safely. So she's at the top. What do? I grab her at the top and I bring her down nice and slowly like that. What I'm doing there is heavy damping. Heavy damping is when a force is applied that doesn't let it even oscillate, just brings the displacement down to zero really, really slowly. That's heavy damping. What if Seren is in trouble and I need to stop her quickly though? I don't have time for her to stop with air resistance or my heavy damping, just bringing it down slowly. I need to stop her as quickly as possible. What I do is let her fall, but then right at the last second, I pull really tightly to make her stop at equilibrium. So she might overshoot past equilibrium a tiny bit, but not much. So here she is, just going along normally, and then I need to stop her, grab her, and then she comes to a stop. That's what we call critical damping. Obviously that would be the one that's most unpleasant for her, because she feels a massive force. When they opened the Millennium Bridge across the Thames, they found that it started oscillating too much, and so they had to introduce dampeners on the bridge to provide a resistive force to the velocity so it stayed nice and still. What's the opposite of that? Instead of having a resistive force, we have a driving force. This is a force that is in the same direction as velocity. What does it do? Speeds it up and it increases the amplitude. Now if I want to push Seren on the swing and I want her to get higher, she's swinging like this. The restoring force is trying to bring her back to equilibrium. But if I want her to go higher, as she goes through equilibrium, I'm going to push, and I'm providing a force when there is no restoring force, and she's going to get even higher. As she comes back down, I'm going to push from the other side, and she's going to get even higher. So we're talking about a force that has the same frequency as the natural frequency, or the resonant frequency. When we talk about natural and resonant frequency, we're talking about what frequency would something oscillate at if there were no other external forces. If this is the case, and it's 90 degrees out of phase with the restoring force, then we're going to increase the amplitude of the thing that's oscillating. And we saw this happen with the Millennium Bridge. That's why they had to install dampeners. What happened? The bridge started moving ever so slightly to the left. What did people do? They put their left foot down to support themselves, and that made it go even further. On its way back, people put their right foot down, which provided a force in that direction as well. And as it got worse, people started balancing themselves even more, and the amplitude kept on increasing and increasing until it shook really quite scarily. Lastly, the driving force frequency doesn't have to be exactly the same in order to increase the amplitude. Once it gets similar to the resonant frequency, then it starts to resonate, amplitude starts to increase. And also, if the driving force frequency is a multiple of the resonant frequency, then it's going to have the same effect. I hope you found that useful. If more, what did people do? They put their left foot down to support themselves, and that made it go even further. On its way back, people put their right foot down, which provided a force in that direction as well. And as it got worse, people started balancing themselves even more, and the amplitude kept on increasing and increasing until it shook really quite scarily. Lastly, the driving force...
Right. Let's do question 1 only. Okay, let's check. It's in a... 1, so M1. Tulum will have max KE. Neat. Right. We're gonna be starting maths now. Right, okay, I think that's it for now. So that's physics revision, chemistry revision, and yeah, I think that's it. Slowly but surely, we are getting somewhere. I am tired as hell. Since my brothers are getting older, I don't have to worry about them making too much noise now. So it's nice. Still a bit of noise in the house, but regardless, it's good. Oh man, I need to finish up the Demon Slayer thing actually. Whoever's actually anyone who comes back to read this, actually, it comes back. I'm actually reading Demon Slayer for my physical manga collection. That's stupid. Yes, I'm reading Demon Slayer, and I'm actually reading, right now I'm reading Tanjiro versus Akaza. Pretty cool fight. Not the best I've seen, but it's cool. I'm entertained, to say the least. Demon Slayer is alright as an experience, in my opinion. Right, we're going back to reading. Is the bathroom even free? I had no idea. I like that. Means my content's going out to more people. We chilling. Alright, that's a Demon Slayer volume completed. I'll probably be starting volume 18 when I can. Hopefully. Yeah, that's another volume towards me completing it. All good. Ibrahim? Ibrahim? Outside, I can hear it. Yeah, not gonna lie, that's been way over 10 minutes. Right. Oh god, my hair's getting longer again. I might need to cut my hair soon. I had a maths. No, you know what? I'm gonna do 20 minutes of maths for today. I did about 10 minutes of extra maths earlier on. So I think that would be the best way to go around this. That's my thoughts. "20 minutes of calling it a day." "20 minutes? I'm not sure if I want to do 20 minutes. Right. We moving on. Moving on to what you say? We moving on to this. Maths. On part 1. My empty water, Alright, so dy dx is equal to minus 10x to the power of 4. Then part 2, y is equal to x to the power of a third. So dy dx is basically equal to x over 3 to the power of minus 2/3. Boom. Right, so 2 ba ba ba. Let's go. Correct. And da 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 na 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 da na 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 da 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 ah da na 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 da na 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 na. So changing ba na 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 da na 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 da na 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 na. Is equal to minus 6. Let's just check. Let's go. Minus 6. And y is equal to 4 root x. So y is equal to 4x to the power of a half. Sol pa sol pa na 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 so na na So let's say this is a chord. Let's say this is one thing, another thing about that. We are meant to find the gradient from A to B. Well, you know what? Screw this. Let's just do change in y over change in x. So I may as well just do 0.3 over 0.5. .6. To the gradient AB is approximating to the gradient curve A. So let's just do dy dx is basically equal to 2x minus half. So let's do 2x to the power of half is going to be equal to 0.6. So in that case, so x to the power minus a half is equal to 0.3. So we're going to turn that into, basically x is equal to 11.1. If I'm correct on this, I will actually be surprised. No, I am not correct. Yeah. So I was incorrect. It's basically just meant to be let's prove from first principles differentiation. Is equal to fx. Over h, which basically just turns into 3. Over h, which basically turns into 3x squared plus 3xh. That's h squared. H is equal to 0, which basically just turns it into 3x squared. Let's go. Da ba da 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 da. 5i basic differentiation. y is equal to log x. Is equal to -1 log. .01. A, B, C. So 2 out of 2, 1 out of 1. Yes? Yes, I do. Yes, I do. Alright.
gonna add this for this.
Huh?
Remember Nad's gonna add this.
Oh, I know. Oh, look. I think that basically makes the stream over now. I am gonna end this right here. We're going over at 4 hours.